this talk, I'm going to be talking about the development of an X-band low-level RF system. So the first part, I'm going to just cover briefly the sort of what Clara is and the X-band RF system, and then I'll discuss in more detail the low-level RF system itself. So first of all, Clara, or the Compact Linear Accelerator for Research Applications, is an electron machine, a normal conducting electron machine based at Daresbury Laboratory. It's intended for the development of free electron laser and other technology developments. So in 2018-2019, the front end, which you can see down here, which consists of a photocathode gun and the first LINAC cavity, was commissioned in 2018-2019, and that achieved a beam energy of about 35 MeV. So now we've installed a further 5 cavities, and work is now ongoing to commission those RF systems to extend the beam energy up to 250 MeV. So there's 7 RF stations. 6 of these are at S-band frequency, 2.9985, and that consists of the gun, 4 LINACs, and a transverse deflecting cavity. And the system that we're really interested in is one cavity at 12 gigahertz, which is a 4th harmonic cavity. So this cavity it's a CERN PSI design. It was manufactured by CERN for us, and it's a linearizing cavity to linearize the phase space, the longitudinal phase space of the electron beam. So this is because there's a curvature imprinted on the electron beam due to the S-band cavities, and this cavity corrects for that curvature by decelerating the beam at a higher harmonic. So we expect to operate at about 30 megavolts a meter, and so we want about 16 megawatts of power at the cavity. It includes some Wakefield alignment monitor ports, and we also intend to operate at about 120 nanosecond pulse width. So that's 100 nanoseconds to fill the cavity and 20 nanoseconds of RF for the beam to interact with. So the RF system consists of a Scandinova modulator with an 8 megawatt klystron, and also a microwave amps solid state amplifier feeding that klystron. And this will provide a 1.5 microsecond pulse into the pulse compressor. Now all the RF stations, the RF systems are on the roof of Clara, as you can see in this system, so that all the systems are above the actual accelerator beam line. So the waveguide will come out of the compressor and go through a labyrinth to the cavity input ports. And finally, we've also got a spiral design load on the end of the cavity as well, which is an additive manufacture design and something that we've been working with both CERN and also a local manufacturer to develop. So we intend to use Libera low-level RF systems for all of the RF stations on Clara. Let me just recap some of the key, what I see as kind of the key parameters. So there's a 3 gigahertz vector modulator, which has a maximum of about 11 dBm. A 3 gigahertz front end, which down converts to 41.6 megahertz. And this system is clocked at 11.05 megahertz, which gives us a time resolution of about 9 nanoseconds. So the key part of my work has been to develop a system that converts between this S-band system and the X-band low-level RF, the X-band RF system. So there were a couple of important design requirements. One was, of course, to maximize the signals coming to and going to the Libera low-level RF. It was important to be able to drive the phase flip on a nanosecond timescale, which is important to operate the pulse compressor, as we'll see later on. And also, we want to be able to resolve and see 120 nanosecond pulses, although the requirement for this is a little bit more flexible, as we'll see. So this is a picture of the detailed design of the front end system. So so this is the section that generates the local oscillator. So this takes the signal from the master oscillator at 3 gigahertz and uses a really high quality tripler to take it up to 9 gigahertz. And then this signal is fed to a splitter, which splits between 9 different channels, 1 for the drive and 8 receive channels. And then this signal is split in between each mixer, and each mixer has its own LO amplifier. So these mixers, they're all extremely high linearity mixers because we want to maximize the dynamic range of the system. And another advantage of using an amplifier for each mixer means that we can take advantage of the directivity of the amplifiers. So that means that we can reduce any crosstalk from between all of the channels. And of course, also because they're such high linearity mixers, they also need a very high LO signal. Secondly, and finally, really, is we took advantage of reflectionless filters because they kind of allow you to have your cake and eat it, really. There are some unwanted harmonic frequencies that needs to be removed from these amplifiers, but we were able to use these filters to get rid of those, but without compromising the match between the amplifiers and the mixers. And it also, additionally, also adds a little bit of padding between them as well, which is very useful. So this is the results, some of the results of the benchtop tests. This is the system, as you can see here, which we've built. And these channels are for the X-band signals, and then these golden channels are for S-band. This is a picture of the output frequency, and it's tested using a signal generator. And this is really good because it shows that there aren't any unwanted sidebands that are coming out of the system as a result of this conversion process. And then this is a admittedly slightly noisy picture of the linearity of the receive channels. I think the signal generator we were using was not especially stable, but it does show that we can use the channels up to 15 dBm, maybe even 17 dBm input, and still get very good linearity without compressing the signal. So, as I mentioned, we need a phase flip to operate the pulse compressor. So, as you can see here, so this is designed to take the 1.5 microsecond pulse, and it becomes about 120 nanosecond output. So this is operated here by this phase flip here in the purple trace. The purple trace. Sorry, I'm getting mixed up. Yeah, it is a purple trace. And so in about the last 200 nanoseconds of the pulse, the phase, you could in theory flip it from 0 to 180 degrees, but unfortunately this wouldn't give you the flat top in amplitude output. So it is flipped from about 100 to 145 and then slowly ramped up to 180. And this provides a flat top output. And this is a simulation one of my colleagues has done. Now, as I mentioned, the requirement for being able to resolve 120 nanoseconds is a little bit more relaxed because we already have power bleeding through the 3 dB hybrid of the pulse compressor. So we will still be able to see what's going on, but obviously we want to be able to see it in a lot of detail. So in terms of implementing this in the Libera system, we have about 17 samples, or 150 nanoseconds to play with and implement this. And as well as that, there is also an amplitude ramp, which is this dotted blue line here. So when the phase flip occurs, we drop the amplitude and begin to ramp it up. And that also provides us with a little bit of control on the output of the pulse compressor. So implementing this in the Libera and taking some measurements we wanted to evaluate kind of what kind of performance we were getting. And so the phase performance is really good. It's not entirely clear what this initial spike at the bottom is, but we're getting the initial phase ramp and then the slope. But in terms of amplitude performance, there is something unusual going on in this the amplitude envelope here. This was a trace that was taken on a pulse analyzer. So then looking at this in more detail in the time domain on an oscilloscope, we can see that for where the phase flip occurs, there is a sudden spike in the amplitude, and then this ramp, rather than being the sort of smooth ramp we expect, kind of has sort of a steps, some ups and downs in it. And so why this happens isn't fully understood. But on the other side of it, looking at this in the frequency domain, from doing an FFT on this data, we can see that there isn't any unwanted frequency content in the performance of this modulator, although there is some unexplained ringing here on the higher side of the frequency domain. So what's next? So we've not engaged with iTech to collaborate over this, but there are a number of areas that we'd be interested in discussing, such as more flexible pulse shaping features, because I know that I think it's APS. You have some flexible pulse shaping features for defining the pulse shape that controls their pulse compressor. And of course, ideally, it would be nice to get an increased sample rate for both the vector modulator and the ADCs as well. We then intend to complete some more system tests with the pulse compressor. So now it says here at low power. What that means is we had the pulse compressor on a bench and just plugged the Libera straight into it. And using the pulse shape that I showed earlier, this is the output of the 120 nanosecond part of the pulse. So we want to optimize this, and of course we hope to test each part of the system sequentially. So we want to test it with the pulse compressor with a load attached to it, and then we can optimize how the system behaves. There is also possibility for including an extra gain stage after the down conversion to 3 gigahertz, but I want to see whether this is really necessary because, of course, it's a trade-off between kind of extra signal on the receivers versus extra noise as well. And whether this is necessary really remains to be seen until we've tested the system fully. And then finally, we're looking at the use of an analog phase shifter, a fast piezo type phase shifter, to perform the phase flip more sort of on a faster scale and maybe taking some of the pressure off the Libera system. So thank you for listening. I'd like to just acknowledge all of the efforts of the team at Daresbury as well, the RF team, and if there's any questions, let me know.
Do we have any questions?
One question, so when you convert to X-band, what's the performance, like the long-term performance? How is it?
You mean when you say the long-term?
Yeah.
When you say
the long-term, like how it acts on long-term?
So I've not noticed. So the system obviously needs some time to warm up, but I've not noticed any long-term drifts or changes.
And the X-band that you're using is for deceleration. So it's basically to correct, to reduce the energy spread of the beam?
Yes.
You do the phase-space rotation technique?
So I don't think it's to rotate the phase space exactly. It's because we're accelerating the beam off crest. The bunch gets a curvature of the 3 gigahertz coming from the 3 gig cavities. So this cavity decelerates it at kind of by using a higher harmonic. Yeah.
Thanks.
Just to get to my understanding, it was a very good talk. One thing I'm not sure I understood. What was your reason to go for your in-house development of that front end? Was it simply not available, or did you find it more useful to develop it yourself? What were the reasons?
Yeah, I think it was that we wanted control. We wanted more control over how it was developed, rather than going for a commercial solution.
Okay. And the other thing is more to the application. So you're using digital LLRF, but what I saw was more like an arbitrary waveform generator, like playback of a desired waveform, or was it not the waveform, but the control which you displayed there on your purple trace?
Yeah, it was the control.
So that was the input to a controller inside. That's my desired phase I want, and then it gets executed by the controller, and then you get the results you later showed in your traces.
Yes.
Okay. And to that end, you are happy with the way how it works?
So I think there's some things that we need to kind of establish in more detail in terms of the performance, but that's one of the reasons we're looking at going down the analog route as well, because there's a lot of other. So, for example, CERN's Xbox system, they use an analog feedback system, and that allows them to get a little bit more kind of control over gaining a flat top output of the system. So we may find in the future that we don't fully use an all digital system, but kind of use a combination of the two.